Welcome back to the next session of electrostatic potential. Friends, today we are discussing about the potential energy, a system of charges. To understand the heading thoroughly, we just recall the definition of electrostatic potential. What we studied there, it is the total work done in bringing UPC from infinity to the point against to the electric field. Now, if I rewrite that equation, I get V is equal to W by Q. That is, electric potential is equal to total work done by the UPC. And if I rearrange this equation, just in the last class I explained about this equation while deriving the relation between electrostatic potential and electric field. If I rewrite this equation, so work done is equal to V into Q. That means energy is equal to, because work done is expressed in terms of joules, so energy is equal to potential into the charge. Hence, in this topic, or the potential energy, a system of charges, I am using the word, instead of U, V, W, I am using the word U, alphabet U, that is potential energy. W, V or U is equal to V into Q, where Q is maybe a unit positive charge or it may be another charge, because it is a system of charges. I repeat once again, so potential is equal to total work done by the charge. So if I rewrite this equation, I will get W is equal to VQ, that is joule is equal to volt into coulomb, that is U. Instead of W, I am using the concept called U. U is equal to VQ. This already studied in the first PUC, that is potential energy. So now U equal to VQ is the fundamental equation in this concept. Now let us start one by one. Suppose if I take a system of charges, I may take any system of charges, but if I want to say it is a system, it must contain at least or a minimum of two charges. So now that is why my first explanation starts with a system of two charges. Suppose if I have only two charges in a system, what happens? Suppose if I have three systems, that will be the B, case B. If I have more than three, that will be another case. Now time being, in this year, we have only two concepts, that is a system of two charges and system of three charges. That will be discussed afterwards. Friends, to understand this concept, first and foremost, we must understand certain things. That is, what is, if I consider the entire board as my space, and this space is completely free from charges, that means what? There is no charge at all. It is completely empty space, or you can say vacuum. In that time, no electric field, no potential, no electric force, nothing is there. Nothing is there in this system. Then, if I consider a point charge, say Q1, if I consider the point charge, say Q1, the charge Q1 will produce the electric field around it. Now listen carefully. Earlier it was a completely empty space. Now I have considered the point charge, say Q1. Q1 produces the electric field around it, called as E1. It also produces the potential, that is V1, so and so. Now, our next concept is, what I have to do, what is the definition of electrostatic potential? It is the total work done bringing UPC from infinity to the point against to the electric field. Now, time being, I kept this charge Q1 at the point, say now A. Now, I will consider another point, say B, at a distance of, say R. So this is point B. At the point B, I want to calculate what is the electric potential. So directly we have to write the equation, that is the potential at the point B due to the charge Q1 is given by V1 is equal to 1 by 4 pi epsilon naught into Q1 divided by, distance here not mentioned, I will mention it as R, then the distance becomes R. Now earlier, I said, once again I repeat, listen carefully, earlier no space, so no charges at all, no charge, no electric field, no potential. Now I place a charge or potential charge Q1. Once if I place a point charge Q1, it produces the electric field around it. At the same time, it also produces the potential around it. Now I am interested to calculate the potential at point B due to the charge Q1 at a distance of R. Then the potential at point B due to the charge Q1 is given by V1 is equal to 1 by 4 pi epsilon naught Q1 by R. Now let's come back to our original situation. So now here is the infinity. At this infinity we have another point, say instead of UPC I have charge say Q2. Suppose if I bring the charge Q2 from infinity to the point B at a distance of R from Q1, what happens? As I said, it is the total work done. So bringing a charge or a UPC from infinity to the finite distance, or say at a distance of R from charge Q1 is the work done, right? So then if I bring the charge Q2 from infinity to this point, then what happens? Work is done. So that work done is stored in the form of potential energy in Q2, right? I repeat once again, the work done is stored, I repeat, I write here, the work done is stored, the work done is stored in the form of potential energy in Q2. Then what I have to write here? Potential equation. What I have to write? Potential equation. Potential equation U is equal to V1 into Q2. V1 is what? Potential at the point B. Q2 is what? Energy stored in Q2. That is U is equal to V1 into Q2. Suppose if I substitute the value of V1 here, what I wrote above, then if I write here, I get 1 by 4 pi epsilon naught into Q1 into Q2 divided by R. This is very, very important. Will be asked for 2 or 3 marks. What they will ask? Derive an expression for potential energy due to a system of charges in absence of electric field. Please keep in mind the word called in absence of electric field. Whatever I am deriving here, it is all in absence of electric field. There is no electric field. Why? What is meaning of no electric field? The meaning is very clear here. Now I have considered a completely empty space or the vacuum. There is no electric field. There is no charge, no electric field, no potential. In that space, I kept the charge Q1 produces the potential V1 at point B. That is written here. Then I will bring the charge Q2 from infinity to the point B at a distance of R. What happens? Work is done. That work done is stored in the form of potential energy in Q2. Hence, the potential energy in Q2 due to Q1 is given by U equal to V1 into Q2. That is U equal to 1 by 4 epsilon Q1 Q2 by R. Next, very important special cases are here. What are those special cases? Case 1 says, above equation, if I refer above equation, if Q1, Q2 greater than 0. As I said, friend, in the first chapter, if Q1, Q2, the product of two charges is greater than 0, they must be alike charges. That means what? They must repel each other. Hence, Q1, Q2 may be plus plus, or Q1, Q2 may be minus minus, or negative charges. In this time, what I have to do is, positive potential energy should be required, or positive potential energy is stored in Q2 due to Q1, or else I can say here positive potential energy is required to bring the charge Q2 from infinity to a finite distance. Finite distance means any distance from the charge Q1 from infinite to finite. Similarly, if I go to case 2, if Q1 Q2 is less than 0, again chapter 1, as I said, Q1 Q2 is less than 0, what happens here? If Q1 Q2 less than 0, then one of the charge is positive, another charge is negative. As I said, so if are opposite kind, hence they attract each other. I can say unlike charges. Hence, negative potential energy is required to bring a charge from infinity to the point P. I think it is clear to you people. So what we have to write here in the explanation part? Consider a charge Q1 placed in a space which is free from electric field in the absence of electric field. Consider a point B or P at a distance of r from the charge q1. The potential at point B due to the charge q1 is given by V1 equal to 1 by 4 pi epsilon q1 by r. Then bring a charge q2 from infinity to the point B at a distance of r. Positive potential energy or work is done. That work done is stored in the form of potential energy in charge q2. Then U equal to V1 q2. So that I can write U equal to 1 by 4 pi epsilon q1 q2 by r. So this is the final expression. That means potential energy due to a system of two charges. If q1 q2 is greater than 0, positive potential energy is required to bring the charge from infinity to the point against the repulsive force, because both are repelling each other, because there is a repulsive force between these two charges. At the same time, if q1 q2 is less than 0, negative potential is required to bring the charge q2 from infinity to the point against the attractive force, because they attract each other. Friends, with this, let's go to the system of three charges. If you understood this system of charges due to these two system of two charges and system of three charges is very easy. So what I will do here, I will go with the next system, that is system of three charges. System of three charges. So this becomes B. So now again what I will do, I will go in another simple manner. Again completely empty space I have considered. So on this board, now at infinity many number of charges are there. N number of charges are there at the distance infinite. What I will do, how many charges are required for us? 3 charges are required. So what I will do here, I will consider charge q1, q2, q3 are placed at infinite. So infinite I can't show here. So for time being, to understand the concept, I just explaining on the board itself. So now first again it is an empty space, no charge. If there is no charge, no electric field, no potential at all. Afterwards, bring the charge q1 from infinity to the point say A. Suppose if I place a charge q1 at the point say now A, I am bringing the charge q1 from infinity to the point say A. What happens? No work is done, because earlier it is empty space. The charge q1 itself produces two things. One is electric field, another one is a electric potential. Then I am interested to calculate the potential at a particular point say B. So now at a distance of say R1. So this is the point B. This is the point B. At the point B, at a distance of say R1, I want to calculate what is the potential. Earlier same concept, it was parallelly. So now the potential at the point B, due to Q1 is V1 is equal to 1 by 4 pi epsilon naught into Q1 by R1. Time being I am writing this R1. Afterwards, what I have to do is, now let's make it a system of two charges as we did earlier. Bring the charge Q2 from infinity to the point B at a distance of say R1. Now I am placing the charge Q2 at a distance of say R1 from the charge Q1. Now I will make it is the distance between the charge Q1 Q2 is R12. It is understanding purpose. What happened? Work is done. So work is done in bringing a charge Q2 from infinity to the point B. What happens is, once work is done, this work done will be stored in the form of potential energy in the charge Q2. Therefore, I can write here, therefore, potential energy of charge Q2 is U1 is equal to, why I am writing U1 means it is system of charges. We have many number of potential energies. First it is only system of two charges, then U1. U1 is equal to V1 into Q2. This becomes 1 by 4 pi epsilon naught into Q1 Q2 divided by R12. The distance become now R12. This is, say, equation number 1. This is the potential energy due to a system of two charges. Suppose if I make it system of three charges, what happens? Very interesting. Look at this. At the same time, if I consider one more point, say C. If I consider one more point C, very interesting. From point A, the point C is lying at a distance of, say, now R13, and from point B, it is a distance of, say, R23. Friends, look at this. This place very, very important. Look at this. In the perception of point C, in the point V of point C, if you look at this, the point C is consisting of how many charges? Two charges. Q1 produces the potential, one potential at the point C at a distance of R13. At the same time, Q2 also produces a potential at a point C due to charge Q2 at a distance of R23. Therefore, how many potentials are here? There are two potentials. So that I can write here the potential at the point C. First I have to write the potential, then let's go to the potential energy. The potential at the point C. The potential at the point C due to Q1 and Q2 is very simple, just like a system of two charges, or a potential energy, a system of charges, as we derived in the previous class. The distance between the potential at point C due to Q1 Q2 is, now I have to write here as V2. At Q2 potential is V1. At point C, how many potentials are there? Two potentials, that is why I am writing V2. First one is the potential at a point C due to Q1 is 1 by 4 pi epsilon naught Q1 divided by R13. So this becomes 1 by 4 pi epsilon naught into Q1 by R13 plus. The potential at point C due to Q2 is again 1 by 4 pi epsilon naught into Q2 by R23. It's over. Next, same procedure again. So now, as we brought the charge Q2 from infinity after writing the potential, now our job is to bring the charge Q3 from infinity to the point C after writing the potential at point C. Now, same sentence again, right? Bring the charge Q3, bring the charge Q3 from infinity to the point C. Therefore, potential energy of charge, potential energy of charge, say Q3, potential energy of charge at C, right? So if I write this, it becomes U2 is equal to V2 into Q3. Why it is V2 into Q3? At the potential at point C, how many potentials are there? Two potentials are there. So that is one potential, two potential, V2. Then I brought the charge Q3. Energy is stored. Please write this as a capital V. So energy stored in Q3 due to the potential V2 is given by 1 by 4 pi epsilon naught into Q1 into Q3 divided by R13 plus 1 by 4 pi epsilon naught into Q2 Q3 divided by R23. This is equation number 2. So now, how many potential energies are there? 2 potential energies are there. How many potentials are there? 3 potentials are there. 1 potential, 2 potential, 3 potential. System of 3 charges, 3 potentials are there. Potential energies are 2 are there. So now I want to calculate what is the total potential energy. So the total potential energy due to a system of 3 charges will be given by total potential energy due to system of 3 charges. System of 3 charges is U is equal to U1 plus U2. What is U1? 1 by 4 pi epsilon naught into Q1 Q2 divided by R12 plus what is U2? This is equation number 2. So 1 by 4 pi epsilon naught into Q1 Q3 divided by R13 plus 1 by 4 pi epsilon naught into Q2 Q3 divided by R23. What is common here? 1 by 4 pi epsilon, take it outside. So if I write this, U is equal to 1 by 4 pi epsilon naught. Let's make it systematic. If I write it more systematic way. So now 1 by 4 pi epsilon naught into, look at this, Q1 Q2 divided by R12 plus, after writing, look at this, 1 to 2, 1 to 1 2, 1 to 1 2 1 2. Now afterwards I will go 2 3 2 3 2 3. So I have to write here the charge 2 3. No? Okay. 2 3 2 3. So I will bring this charge this side. So Q2 Q3 divided by R23 plus 1 2 2 got over, 2 2 3 got over, now 3 2 1. So it is now Q3 into Q1 divided by R31. This is the potential energy system of how many charges? 3 charges. It is completely cyclic. If you look at this equation, U is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12 plus Q2 Q3 divided by R23 plus Q3 Q1 divided by, look at this, 1 by 4 pi epsilon into Q1 Q2 divided by R12 plus Q2 Q3 divided by R23 plus Q3 Q1 divided by R31 or R13. You can write in any manner. So this is how the potential energy of system of 3 charges will be derived. So friends, in the examination, they concentrate on 2 charges. If they want to ask for theoretical concept, if they want to ask for theoretical concept, they will go with system of 2 charges. That is, derive an expression for potential energy due to a system of 2 charges in absence of electric field, means this one you have to write. Or else they encounter a problem or numerical, a charge is consisting of 3 charges at a distance of, say, making a triangle or corners of a triangle ABC, then calculate the total potential energy system of 2 charges. Just use this formula and arrive at the answer. Thank you.